Hello everyone. Today, I would like to present one of our recent research in the general area of the fusion of mechanics and machine learning, a data-driven method to automatically discover the variational equations hidden in physical systems, only from captured discrete data. I will first introduce the background of this work, the existing researches, their advantages and disadvantages, and then present the methodology of this method, and applied it to rebuild variational equations for several physical systems. Han-Qing Jiang at Arizona State University collaborates with me in this project. As we all know, abstracting equations from measured data plays a pivotal role in scientific discovery. For instance, Kepler distilled the laws of planetary motion based on Brahe's observation data. Undoubtedly, the manual extraction of equations from captured data has laid the foundations of science. However, it's a quite difficult task. It always requires massive investment of time and resources, and more importantly, an engineer's imagination, which is likely to have but hard to ask. Recently, with the advancement of data science and computing technique, we can not only collect, record, store, and simultaneously analyze massive discrete data, but also automatically extract equations from measured data. There are two mainstream methods to discover the governing equations. That is, symbolic regression method and sparsity-promoting optimization method. In symbolic regression method that was developed by Schmidt and Lipson in 2009, they first preselect mathematical building blocks such as library of functions, algebraic operator, constants, and state variables, and then search the space of mathematical expressions to minimize matrix of error, which balance model complexity and prediction accuracy. This method has successfully extracted Hamiltonian, Lagrangian, and the governing equations of motion for several fundamental physical systems. However, it involves arbitrary selection of library of functions and is extremely time-consuming and sensitive to measurement noise. In sparsity-promoting optimization method that was developed by Bruton's group in 2006, they first preselect state variables and basis functions, and then express the first-order derivatives of state variables as linear combinations of basis functions. Finally, solve the undetermined coefficients of linear combinations by sparse regression, which balance model complexity and prediction accuracy. This method is quite efficient, though it is still limited by the arbitrary selection of basis functions. Both symbolic regression method and sparsity-promoting optimization method belong to the pure data-driven science. Recently, a new paradigm for scientific discovery emerges, which is theory-guided data science. Insert appropriate knowledge into the pure data-driven science may improve the efficacy of pure data-driven methods. But what knowledge we should insert into physical systems? The knowledge inserted should be applicable to many physical systems. Our answer is variational principles. Variational principles are the most ubiquitous principles in physical fields, ranging from classical mechanics, relativity to optics, to name only a few. The variational principles state, for a general physical system, the actual motion q, obey an integral variational equation Here T1 and T2 are arbitrary lower and upper bounds of integration. U0 and Uj are functions of system attributes S, motion Q, and its derivative co-dot. U0 possesses the dimension of energy, while the dimension of Uj is determined by dimension of motion Qj. Qj are arbitrary variations of actual motion with constraints at lower and upper bounds of integration. U0 means the variation of function U0 induced by variations of actual motion Q. Consider a fundamental problem in Newtonian physics, a free-falling object under the field of gravity. The Lagrangian L is defined as the difference between kinetic energy T and potential V. We can directly write the variational equation and its equivalent equation by comparing with the general formula of variational principle. We can obtain the integrands U0 and U1. Here, the integrands are functions of system attributes M and G, motion Q, and its derivative co-dot. By inserting the variational principles into physical systems, the objective to discover physical equations from captured data comes down to determine the integrands U0 and Uj as functions of system attributes, actual motion, and its derivative. As we know, the variational equation has an equivalent differential equation, that is, Euler-Lagrange equation. Here, let's briefly compare the discovery of variational equation and differential equation. In the variational equation discovery, we extract the integrands U0 and Uj, while in differential equation discovery, we extract the functions fi of motion, its first and second derivatives. The variational method only involves the first derivative estimation, while the differential method involves the second derivative estimation. Furthermore, the variational discovery includes integral operation, while the differential discovery does not. Thus, the variational discovery may possess higher robustness to measurement noise than differential discovery. Here, we briefly illustrate the whole process of this method. It consists of 6 steps. Step 1. We determine the constant motion Q, such as the displacement for a mechanical system and the current for an electrical system, and then identify system attributes which may influence the motion, such as mass, damping, and stiffness for a mechanical system, and capacitance, inductance, and resistance for an electrical system. Step 2. For integrands U0 and Uj, according to dimensional analysis, we construct associated parameter clusters constituted by system attributes, constant motion, and its derivative, and then express the integrands as linear combinations of parameter clusters, with unknown coefficients to be determined. Step 3. Collect the discrete data. Step 4. Generate arbitrary variations of motion under constraints. Step 5. Substitute the linear combinations of integrands, variations of motion, and discrete data into the variational equation, and then perform integration to obtain a linear algebraic equation with respect to unknown coefficients. Step 6. As a final step, by changing the lower and upper bounds of integration and the variational style, we get overdetermined linear algebraic equations. Solving it by pseudo-inverse algorithm yields the coefficients of linear combinations, and then the analytical expression of integrands. illustrate this method by an example of free-falling object. Our objective is to rebuild the variational equation from data. In step 1, the concerned motion is set as the coordinate of the particle, and the attributes are set as mass and gravitational acceleration. In step 2, we construct the integrands u0 and u1 by dimensional analysis. We first write the dimensions of integrands, system attributes, motion, and its derivative. Then, constitute parameter clusters with dimensions of u0 and u1 by system attributes, motion, and its derivative. Finally, express the integrands and linear combinations of parameter clusters by substituting the linear combinations into variational relation and arranging according to the variation of motion and the variation of its derivative. We obtain new integrands with constant coefficients C1 and D1 to be determined. As a simple example to illustrate the application of this method, in step 3, we capture discrete data from the exact solution rather than experiments. In step 4, the variation of motion is set as a special form, in which the factors t minus t1 and t minus t2 guarantee the constraints at the initial instant t1 and final instant t2. In steps 5 and 6, we substitute the discrete data and the variation of motion into the variational equation, perform the integration numerically, obtain the linear equations with respect to coefficients C1 and D1. Solving the equation yields the values of coefficients. It's obvious the variational equation discovered coincides with the exact one completely. To summarize, the discovery of variational equation of free-falling object includes 6 steps. Step 1. Identify the concerned motion. Step 2. Construct the integrands by dimensional analysis. Step 3. Capture discrete data. Step 4. Select a variation of motion and constraints. Step 5. Constitute linear equations with respect to undetermined coefficients. And step 6. Solve the linear equations. We also discussed the robustness of this method to noise and the requirement on data amounts. Researches show that due to the integral operation in the variational equation, this method possesses high robustness to measurement noise. Due to the arbitrary of variation styles and arbitrary of integral intervals, this method has less requirement on data amounts. Furthermore, by capturing discrete data from the same system with different parameter values and different initial conditions, the efficacy of this method is dramatically improved, because this discrete data provide more information of system itself and reduce the adverse influence of measurement noise. This slide summarizes the cases we have studied, including the relativistic particle moving in an electric field, Van der Waals system, Duffin oscillator, and a 2-degree of freedom dissipative system. This method successfully rebuilds the variational equations for all these cases with high accuracy and high efficiency. In the case of relativistic particle, the exact variational equation includes radical expression. This method discovers its expansion successfully. In the Duffin oscillator and 2-degree of freedom system, this method successfully discovers the external inputs and dissipative terms. Here, we discuss the relation between this method and the finite element method. The finite element method starts from variational laws, partitions the spatial domain, and obtains discrete data by solving linear equations, while this method starts from discrete data, partitions the temporal domain, and obtains the variational laws by solving linear equations. Thus, this method can be regarded as the reverse process of the finite element method. Conclusions. We developed a data-driven method for automatically discovering variational equations in physical systems. Due to two features of variational principles, the compact form and holistic viewpoint, this method has two intrinsic advantages: robustness to measurement noise and less requirement on data amounts. That's all for my presentation. Thanks.